Okay, here's the final part of chapter 6, which is about describing motion in more than one dimension. So we're mainly going to concentrate on 2 dimensions. We are for the notes here anyway, because that's what you'll need for the exams. However, it's just as simple. It's the same mathematics as doing things in 3D. So we're going to look at this idea, this shape of how things really tend to move during gravitational motion through gravitational fields. So if we did have a diver like this, and there's plenty of video little clips that I put in the lessons to see, they're actually all going to follow exactly the same path. And this path has been known about since the days of Pythagoras and Archimedes. It's just trying to describe that. Interestingly enough, until Galileo did the mathematics of this in Europe, they didn't think this was the case. So, back to our Hanna-Barbera cartoons. So what we've got is an inertia of an object. So if we fire something, throw something, whatever it may be, it's going to go up, usually with some sort of diagonal, maybe almost straight up, might not be straight up. It might actually fire something vertically while it's on the back of something moving horizontally. You'll get the same motion. If you were stood on a train and you were throwing something in the air, for example an orange, just a little bit in and out of your hand, as it went through a station, the people outside on the platform would see your orange do this, but to you it moves up and down. So I've got some short little practicals for you to try out, because actually the mathematics of this is exactly what we've had already. So quick reminder, these are still true. Okay, the only thing while it is flying through the air, that's the crucial bit, so not whatever's making it go, not what's making it stop, but while it's flying through the air, it has just single acceleration, at least in an ideal world. So if we ignore drag, ignore air resistance, ignore fluid dynamics, ignore wind and other things, then there is only a single acceleration, and that's downwards due to gravity. So all these equations work. Okay, that one is really useful. We will use it a lot, but it's not the only one, so it depends again what information you have. So stick with the practice on these, and of course we may have that as well. The one that we usually don't tend to have is the one without an acceleration in. Okay, so we're going to stick away from that, because we normally have that as a piece of hidden information. So, you take a running leap off something and you fall into the water, you're still going to follow this path. If you don't go up at all, you'll just follow that the path. Okay, so the path will always be the same. There'll be a point at which something is not going up, but is just falling downwards due to the acceleration due to gravity. When it's going upwards, it's slowing down because of the acceleration due to gravity. Okay, but if it's straight up and down, it will stop, then come back down. Here, it's still going to be moving sideways all the time. So when it stops going up and starts going back down, it is still moving sideways. And that's the crucial idea of it. It's all about thinking of things in 2 dimensions. Okay, so we're going to break things down into how much its motion is upwards and how much of it is sideways. And if we work on that, that will always work. Okay? So, we'll start with the hardest case. These tend to be less common than things being thrown off a cliff, or someone jumping or falling off the edge of a table. So this could be your toast falling down, for example. If you think about that, then what we need to do is actually break into that component area. So how much is upwards, how much is sideways? And of course, the normal thing is we would measure the angle from the horizon, because you can see how far up you're throwing it. You don't say how far down from vertical. So angle nearly always tends to be that one. In which case our horizontal component, okay, which I'm going to call U, because it's at the beginning. Okay, so here is U on my diagram, that's my initial velocity. So U horizontal, which we'll shorten to H later, is u, the multiplying factor, the hypotenuse multiplied by that direction, which is cos. Okay, and u vertical is going to be again u times, but the other component gives the other trigonometric function. Okay, so all you're defining is the sine or cos of the angle and scaling it up by whatever size you've got there. Now, the interesting bit, I think highlighted quite well in this diagram, is that if we actually look at the motion of things, if we could freeze them over time, if we fire something horizontally, it would go sideways, actually at a steady rate. Every second, the sideways motion doesn't really change. Again, ignoring air resistance. So why is that? Well, if you think about it, there's no sideways acceleration. Okay, so using this scale, yeah, it's going sideways at a nice steady horizontal velocity. Why? Because there's nothing to speed up or slowing down. If we have air resistance, then yeah, that will change over time, because that will cause a force to make it change its motion. But downwards, we have, of course, on any point, our force that's making it accelerate. Okay, and so if we have something going sideways, well, we'll actually have exactly the same motion as if it's falling downwards. Okay, so the vertical height, or perhaps more accurately, the vertical drop in this case, is going to be exactly the same every single point of motion. Doesn't matter if it's going down or sideways, it's going to be the same vertical height. Why? Because you've got that acceleration due to its weight downwards, here and here. Okay, so let's just put it on there and make it a bit obvious. So because it's the same mass objects, it's going to have the same amount. From what we showed right at the beginning of the chapter, that same force is going to accelerate that same mass, and the mass cancels out. So actually, it will accelerate downwards at 9.81 meters per second squared, whatever the mass is. Okay, so it doesn't matter if the cannonballs were different, you will find the same effect. Now, quick experiment you can do with this is nice and easy. Get yourself a ruler, and all you need is 2 coins, one on the end, and the other one you're going to put next to it. Okay, now what you'll need to do is, if you put one next to it and one on the end at the other end, hang one off the edge of the table, and what you're going to do is just smack it around. So with your finger as a pivot in the middle, give it a tap. The one that is sitting on the top will drop off the edge of the table, so drop straight downwards. The other one, if you get it to hit sideways, so it goes off the table, okay, you'll hear that both of them hit the ground at the same time. And it doesn't matter how hard you smack that, so how far it goes sideways, you'll still hear them hit the ground at the same time. Which shows that, as I've said here, the motion vertically has got nothing to do with the horizontal motion. They're completely independent. Now that makes the maths beautifully simple. Okay, but I'll do that at the end. Okay, so I'll bring up some ideas. So, crucially, the ideas that matter are, vertically is one thing, but horizontally you have no accelerating force. Okay, so there's no acceleration, no force. Okay, so that's the reason you have no acceleration. Oops, sorry, I've missed a few letters out there. Acceleration, no force. Why? Let's just say ignoring drag. Okay, so what we've got is, if we're ignoring the air resistance, the wind, etc., that just means that, golden rule, a lot of space I've put here because I want it to make it stand out, horizontal velocity is constant. crucial. Okay, whereas vertically, the acceleration due to gravity, or due to the gravitational field, equals, again it varies around the world, but for all our questions, equals 9.81 meters per second squared. Okay, so 9.81 newtons on every single kilogram will ensure that amount of acceleration. So what does that mean? It means that if we go back to that picture, or the idea of the picture, my gaps are getting bigger, and the displacement each second is getting bigger, because if we go back to our Suvat ideas, it's because the motion depends obviously on the time. And if I just take that equation for the time, can I find it? Can I heck? If we look at that detail, there it is. Then the equation where displacement depends on time is this equation here, and it's time squared. So if time is doubled, you're going to go 4 times further if you're starting from rest. Okay, so the increase in distance is going to get 4 times bigger. So the velocity increases. Okay, that's a crucial idea, but quite hard to describe. So 9.81, okay, meters per second squared. Let's just put that in. Okay, so what that means is that your displacement, displacement increases with time by s equals half a t squared. Okay, so notice I'm doing the increase. I'm not looking at the overall, so I've ignored the first term. But if you start at 0 speed, if you just drop down, then yeah, it's still true. So that is a crucial one. Okay, in terms of what you need to do here, you will need Suvat equations. Not up here, because that is not accelerating, it is just speed, distance, time. Okay, so that one's nice and simple. This one's the more complicated one. Okay, and crucially, vertical and horizontal motion do not affect each other. However, and this is the important bit, as we have seen from the picture in my last little sketch, the time it takes, for example, for this cannonball or these cannonballs to hit the water is the same. Okay, so in other words, they take the same time. But, this is crucial, happen at the same time, and therefore take the same total time. So that's your clue with how to make things work. Okay, and on my picture here I've got this horizontally, but if I was to look at something, dropping, just only dropping, if we were to throw things up, and again, like person, here's my orange on the train, little boy throwing it in the air, well, from the outside, he's obviously dropped it because he hasn't just caught it. But yeah, it follows that parabola. It follows 2 halves of the same curve. Okay. Now, for those that are mathematically minded, if I just turn that upside down a second, you may recognise that. That's a y equals x squared, or proportional to x squared curve, because In this version, the y is on the on the vertical axis. Okay, how far has it gone? So that's my displacement, and time squared is kind of that idea of the horizontal axis. Now it's obviously not a graph, it's actually motion, but the same idea still runs. Excuse me, getting lots of beeps going on over there. So, how do we make that work? Well, the simple thing is we need to work through the principles separately. Okay, so in my picture here, as I say, we have S equals ut, and here I've got S equals half AT squared. Okay, that's my change, and I should say that change is there. This is overall from the beginning, so that will always be true. However, this displacement goes up and then it goes down again, so it can get quite complicated. However, the maths does not change. So what's the technique to use while doing this? Well, just the same as we had before. Okay, and the best way is just to try this. So what we will do is always start the question with your information, but, and this is the crucial bit, and this is why you need to lay it out like that, you need to find out what these are vertically, or which ones you have vertically and which ones you have horizontally. Okay, that will be the same. Okay, because it's going at a constant rate, it's not going to change the velocity. That's just going to be that original u. That doesn't matter. A equals 0. It always does because it's not accelerating. So all we have is SU and T. T is the same. Okay, so when you're doing your practicals, when you're doing your practice or with the questions, you will need to work out the time to work out the other one. Now normally 99.99999% of the time you'll need to work out the drop. Okay, so you'll need to work out the vertical bit part first. So this is usually first. Okay, it's only really when if you get onto degree level then sometimes you work it backwards from the final result. But normally it's that one. And then you work that out second, because it will often be how far does it travel before it hits the ground, or will it hit the ground, or type thing. Okay, so that's how you do it. Simply work through at the steady rate. Some of the information you'll have, some of it you won't. Crucial bit you'll always have, minus, going downwards, 9.81. Okay, and that's how to do any of these questions. They're really straightforward. Just do it logically. Find out what you've got for S, U, V, A, and T. T will normally be found from the others, not always. And then you will find out the missing value, which will usually be that or that, from sharing the time across, the same time across. Okay, if you had it even more complicated, like we've got this, well, again, it just goes back to that starting point where we had the idea of, there's a hell of a mess in here going on, there we go, where we have, perhaps we need to find the component. So if it's a diagonal, then we need to find the horizontal and vertical value from that if you are given an initial angle. But once you've got those, stick it into the SUVAT table. Okay, so maybe you put it in, maybe you don't. Maybe you put in u cos, yeah, and sorry, this is vertical, so sine, etc. If it's one of these, then what you can do is you could find a value to get halfway to, i.e. where it stops, and then double it. But of course, that's not symmetrical, so you can't do it. So actually, just put the values in. If it's upwards, it's positive. It's downwards, it's negative. You will still find the total, for example, horizontal displacement. If you are going to use u, positive, acceleration, negative, and things like that. So it'll still work out. Try it. You'll find that it's quite impressive because it doesn't seem logical. Lastly, worth putting in that, okay, there are other factors, but air resistance that we're going to look at changes with speed, so you cannot just take it off. It will vary through the journey. So what you'll actually tend to find is that at the beginning you get the most effect, and then it tends to fall more vertically at the end because the drag has stopped it going so far sideways. So yeah, more vertical at the end, slightly more curvy at the beginning, but the effect is small. And that's all there is to parabolas. You need to go and practice them. That's the only way to get good at them. So if we flick through some questions right at the back, I'll get into this kind of idea. You'll see from mine how I do it. Okay, so this one, for example, we're just assuming it's going sideways. So horizontally is where you're going to get your motion. We have no velocity at the beginning. Vertically, because it's just going sideways. Okay, it's not going down to start with. So u at the beginning downwards is 0. You don't know the speed at which it hits the sea, etc. This bit more awkward. You've got a projectile. So projectile definition is something that does not have its own motion. So it does not have a rocket or an engine or anything like that. So a football kicked is a projectile. And if you launch it at 45 degrees with a certain speed, then you can start to break it down, etc. Okay, this one is just after the height, so I haven't gone into the detail. But again, a little sketch so you know which letter you're trying to find and where is it and so on. Okay, and more importantly, someone marking your answers will go, H, that's what they're after. So he says not using that. S would be better. There we go, put that in now. Maybe we'll scrub that. Yeah, scrub that. So S, I'll neaten it up in mine. Here we got others, and we got the idea of changing it, so adapting around it, and then we build up to near the end. Again, we're just starting to get different things, but it's all about the idea of keeping vertical away from horizontal. Okay, so these are really just to check your thinking, check your ideas are clear, because there's quite a lot of descriptive stuff. Most of our questions are calculations. Okay, so we'll finish up there, practice these questions, and then go on to actually practice the homework questions.